Hi, it's Dr. Z. In this video, I will review zScores. By the end of this video, you'll be able to describe zScores and explain the purpose of zScores in research. Do you have an older sibling or relative with whom you are super competitive? Do you compare exam scores to see who did better? If you each are taking different classes with different instructors, you cannot compare the test scores equally. It's like comparing apples to oranges. That's where zScores come to the rescue. A z-score is also called a standard score because it provides a standard scale of measurement for any variable. This allows for easy comparison between different types of test scores. Z-scores are also the first step into inferential statistics. Let's imagine the following scenario. You earned 76 on the statistics exam. How did you do? What information about the exam would you want to know first in order to make an interpretation? Let's imagine this first scenario. The mean or class average was 70 and the standard deviation was 3, which means that your score of 76 falls way up here, meaning you did extremely well compared to the rest of the class. Nice! But what about this second scenario? Here, the mean is still 70, but now the standard deviation is 12. So your score of 76 falls, well, better than the average, but you could have done better on the exam. In this scenario, knowing the mean and standard deviation are helpful pieces of statistical information to make interpretations or inferences about the data. When comparing two different sets of scores, we need a value that puts the scores on the same level. The purpose of z-scores is to do just that. Z-scores better describe a score's location in a distribution without needing to know about the mean and the standard deviation. In other words, z-scores form a standardized distribution for direct comparison with different values. Your exam score in statistics is like an apple, and your exam score in, let's say, anatomy is like an orange. They are two different sets of scores, so we cannot compare apples to oranges. But what if we can turn that stat score into a pineapple, and then turn that anatomy score also into a pineapple? We now have two pineapples, so we can compare the two directly. Z-scores allow for converting scores into pineapples, or standard scores, so we have a way to make them comparable. A single score is a number value that describes the number of standard deviation that an X-score is above or below the mean. It is also referred to as a standard score because a z-score transforms an X-score into a standard scale of measurement. As a result, you need to know the mean and standard deviation for the data set to determine the z-score. So, what does a z-score even look like? A z-score is a signed number that reflects the original X-score. Let's use z equals plus 2.00 as our example. The sign refers to whether the score is above or below the mean. A plus sign indicates above the mean, and a negative sign indicates below the mean. The number value of the z-score represents the number of standard deviations the X-score is from the mean. When put together, the z-score here of z equals plus 2 means that the original X-score was 2 standard deviations above the mean. If this was your statistics exam score, you did awesome. When z equals 0, that means it is exactly in the middle of the normal distribution, or at the mean, z equals 0. Because z-scores are a standard score, we can graph them. This graph is a distribution of z-scores. Recall that distribution is just a fancy word for a table or graph. Also recall that a normal distribution is a bell-shaped curve, unimodal, and symmetrical. Therefore, the mean is always in the middle of the distribution. The dotted lines here indicate that there is one standard deviation in between them. Now at the mean, z equals 0. And a z-score reflects the number of standard deviations that a z-score is above, or an x-score, is above or below the mean. So one standard deviation above the mean is +1. 2 is a +2. And if we go below the mean, one standard deviation below is -1. And 2 standard deviations below the mean is -2. Now that we've introduced z-scores, are you ready to practice your new knowledge? I have 2 examples for you to review. The sample of anatomy exam scores has a mean of 60 and an SD of 10. I want you to draw the graph of z-scores with the corresponding x-scores. Think back to the previous chapter where you learned how to graph mean and standard deviation on a normal distribution. Once you've completed the graph, answer these questions. Please pause the video and complete these problems on your own. Resume the video when you're done to review your answers. Ready for the answer? First, let's draw in the dotted lines. The SD is 10 and the mean is 60. One standard deviation above the mean is 70, and then 2 is 80. If we go below the mean, 1 is 50, and 2 standard deviations below the mean would be 40. Now we should just include our standardized z-scores. Now we're ready to answer these lecture examples. Question 1 asks, what is the z-score for x equals 80? Based on the graph, you go to x equals 80 and then scroll down to its corresponding z-score, which is z equals +2. Question 2 asks, what is the x value for z equals -1.50? Based on the graph, you should go to z equals -0.50, which is right around here, and then you'll scroll up to the corresponding x value, which is right between 40 and 50, which is x equals 45. When you have nice whole round numbers like these for the mean and standard deviation, you can easily use a graph like this to answer similar questions. However, in the real-life world of statistics, we use a formula to calculate z-scores. Stay tuned for the next video that explains how to calculate z-scores. In summary, z-scores provide a standard scale of measurement for easy comparison between different types of test scores. Z-scores make it easier to compare apples to oranges. Z-scores serve as a transition into inferential statistics and are an important Lego building block in understanding statistics.